All right, thanks again to everybody for joining today. We had a little bit of a gap in the talks, but we have a couple now in a row. So I'm happy to invite back Jeronimo from Florida International University, who I think has presented 4 or 5 times. So I don't know if you get the award for most presented, but whenever he comes, we always have a really good discussion about all the projects that are happening at FIU and at AmLight and Ampath. And this is a bit of an update because I think we had a talk on some of the telemetry work that you've done in the past, but I think that this will be a good introduction if you haven't seen it yet, and a little bit of a discussion about where you guys are going to be taking this project into the future. So I will turn it over to you, Jeronimo, to walk us through it.
Good afternoon, all. Thank you, Jason. That was a great introduction, and that's exactly it. We had this product called AmLight-INT that I presented in 2019, and that when we presented we presented the idea, very small results, and then in 2021 we presented it 2 years after that. So everything that we accomplished, all the challenges that we addressed, and I thought that well, it would be good to have a wrap of this project. The idea is, well, what happened since 2021? That was in January 2021. How we're using this, what happened to that solution that I presented. So this is the scope, is the final part. I'm still going to go a little bit through the introductions for those who never heard about INT or stream telemetry. For those who have hanging there, there's new content here that I think is going to be worth going through the introduction again. So I will keep presenting in this presenter mode. I'm not going to put presentation mode because I'm going to be alternating with the browser where I want to show real data. So this is the outline. I'm going to be introducing AmLight, talk a little bit about the science driver that motivated this project. Specifically talk a little bit about In-band Network Telemetry, or INT, the challenges that we had with developing the solution and the challenge that we have with INT itself, a little bit of the deployment, the environment. I'm going to show a little bit of the screens of what we have in production, talk a little bit of the Supercomputing 21 demonstration, and also a little bit about the future. So for those who never heard of AmLight, AmLight is a distributed academic exchange point. It's funded by the National Science Foundation and collaborators in Latin America and Africa. The official name of the project is AmLight Express and Protect, and it's part of the IRNC program from NSF. Currently has 600 gigabits per second of upstream capacity between US and Latin America, and it has an 100 gig link going to South Africa. So the topology that you see here on the right side reflects exactly what we have in production. All of this is managed through an SDN infrastructure. So we have SDN controllers, all the switches in all those locations are SDN switches. Some of them are OpenFlow 1.0, some of them are OpenFlow 1.3, and there's a little bit of experimentation, the barefoot runtime. We have points of presence in Florida, 3 of them, 2 in Brazil, 1 in Chile, 1 in Puerto Rico, 1 in Panama, and 1 in South Africa. And soon we're going to have 1 in Georgia, Atlanta, Georgia. And since the talk is about INT, I want to explain what is the science driver that motivated us to do all this work. So for those who never heard, there is a project called Vera Rubin Observatory. It's also partially funded by the NSF. And this is used to be called the LSST, the Large Synoptic Survey Telescope. It's a huge telescope that is going to be installed in northern Chile that uses AmLight to get the traffic into the US. And this project has a very strong SLA, a service level agreement. And that service level agreement was the thing that motivated us to go towards INT. And what was that? So this one requires a little bit of animation. So this is the Vera Rubin data transfer, how the workflow, it's called the workflow. So every 27 seconds, a picture is going to be taken from the sky. This picture is going to be partitioned, it's going to be processed. There's just metadata that's going to be generated from this picture. And this picture is going to be sent to, this point is going to be sent to Slack in California. So there's this quiet period, there's no data transfer. Then we have 5 seconds of up to 40 gigabits per second of data transfer. This it has a total is 13.6 gigabytes. And then goes back to picture processing, blah, 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 and then data transfer. So this is going to happen all night long as it's dark. So what is our concern? The tolerance in the SLA for packet loss is very, very minimal. It's then 1 out of 1 billion packets. And imagine that you have a condition that is now leading to packet loss that happened in the interval of one of those data transfers. So based on the technology that we had back in 2018, when we started this project, that was more like everything was using legacy technology, everything was a lot of manual activities. It's impossible that we're going to solve whatever condition that is leading to packet loss in less than 20 seconds. So it's very possible that the next data transfer is going to be affected. So the next one and the next one, as long as it takes for the engineers to wake up, get their coffee, get into the CLI and start troubleshooting all of this. And most of you have been experienced this kind of situation. Mitigating packet loss sometimes can take days, sometimes even weeks. So this is one of the things that motivated us. So how can we understand what is happening, have a more deterministic view of what is happening, and try to create a solution that would mitigate this right away. So this is where INT was considered, because INT is a solution, is an application from the P4 language that adds the telemetry of all the telemetry per node in the path for every switch. The telemetry that that switch has is added to the packet. So you get to monitor every packet that traverses the path between 2 points of the network. And so every switch will add telemetry to that packet. Is going to be done by the data plan. That's not done by the CPU. This is done by the same chip that forwards the packet, which means that in the end, you can track or monitor or evaluate every single packet at line rate in real time. There's absolutely no impact to the control plane. So every other function that you have, like SNMP, SSH, BGP, OSPF, none of this got impacted by having telemetry. Even exporting the telemetry is done directly by the data plane through the use of programmable chips. So there's a lot of telemetry that those devices can support. In our case, we use timestamps, ingress port ID, egress port ID, Q, buffer utilization or Q occupancy, sequence numbers, and many others. So depending on the technology that you're using, depending on the chip, you can have a wide variety of options that could go from wireless to switch to 100 gig port. So in our case, that's what we use. And we're going to talk a little bit more about that. So this is how INT works. Pretend that there's 2 nodes, one on the right side, one on the left side, node A and node B. Those are normal computers or normal routers, devices that are not aware of INT. So node A is sending a packet to node B that's represented by the red arrow or the red line here. So the first step is node A is going to send the packet, and the first switch in the topology is called INT source switch. This one is going to add the telemetry header and telemetry data. The header has the instructions that notify the other switches what kind of instruction or what kind of information to add to the telemetry header or to the telemetry data. So then you can see the next switch adds more telemetry. The third, the fourth, and the fifth switch adds telemetry, but the last switch in the topology here is called INT sync switch. This is going to remove the telemetry. It's going to bring the packet to its original format, forward to the destination, in this case, node B, and then wrap that telemetry into a report, like into another header, and then send this with the TCP/IP header to the telemetry collector. So this telemetry collector, which is just a computer connected to the switch, we receive the telemetry that came from that packet plus the TCP/IP from that packet, and a little bit of a header information that has timestamps, it has sequence number, it has identification from the switch. And using that information, then the telemetry collector could do its magic. And it's important to emphasize this. This happens per packet. It's not per flow, it's not sampling. This is for every single packet. So what can be done, or what is that we're doing at AmLight? So with the solution that we built, we can have instantaneous ingress and egress interface utilization. So since the data comes from the packet has the packet length, and then you know the ports and the switches, then you can do the interface utilization, but not just based on the specific metrics like interface ID. You can do interface utilization using the queue number. You can do based on the VLAN, you can do based on TCP/IP, any combination based on the fact that you have the header of that packet and you have the counters for that packet. So you can do monitoring bandwidth utilization many different ways. And the most important part here is that you don't have to ask the switch for that information. There's no need to wait. That packet is sent to the collector. So the collector knows right away. If you have enough precision in CPU, you can do bandwidth utilization between two packets, because then you know everything that passes through one specific interface. And all the timestamps that are provided are nanosecond time scale. You can do like instantaneous egress interface queue utilization, or we call a buffer. So you can see where's the queue occupancy or queue utilization or buffer utilization per packet. And this is very helpful if you have QoS policies, if you make use of multiple queues because you have priority for voice over IP traffic, or for, I don't know, Zoom traffic or data transfers, or even routing protocols, for example, or SSH, this kind of stuff. So then you can use this to validate your policy. And since packet drops are created because those buffers get to the limit or close to the limit, now you can kind of anticipate that you're going to have packet drops because you're monitoring the buffer in real time. You're monitoring the buffer per packet. So you know that that buffer is increasing, and eventually you know as a memory that we're going to run out of space. You can have per node hop delay. So every switch will add the timestamp of when the packet entered and when the packet left the switch. So this, it's a great information for you to try to identify where the jitter is in the data transfer, because we know jitter is the variation of delay. Jitter is very bad, especially for voice codecs. And you want to mitigate, you want to minimize the jitter, and you want to know where the jitter is coming from. So if you have 30 switches in between 2 points, it's very hard to understand what switch introduced that jitter. The difference with INT is that the switch will tell you exactly how long it took for the packet to be forwarded by that node. So you know exactly where the source of jitter is, and which could be more than one. Again, this is also very useful for mitigating traffic engineering issues. And you can have layer 1, layer 2 path tracing. So the thing here that INT does that independent of the technology. So you can have the port number that was used for the switch when the switch or the packet entered the switch, when the packet left, even the tunnel ID. So let's say that you have a tunnel, or you have a link aggregation, or you have ECMP, or whatever technology that does load balance. Now you get to see the physical port or the link aggregation port member, and you get to see the lag as a whole. So this is great for you to track the path, exactly what was the path taken by a packet back in time. So you can see 2 weeks ago, 1 in the morning, then you can see, oh, this packet was going through that port of the lag. So when the user complained there was a packet loss, the most important part for you to understand is what was the path taken at that point in time, because that's how you're going to start the troubleshooting. If you don't know what was the path taken by a packet or by a flow, it's very hard to start this troubleshooting. But now you have this, and you can even have the egress QID. Not just the physical ports, but you also know the physical QID or the physical buffer that was used at that point in time. So instantaneous ingress and egress interface utilization. I want to show this like very quickly, the difference between the same data flow between when monitor using INT and when monitor using SNMP. So this graph on the right side has on the top the visualization provided by an INT, and the one on the bottom provided by SNMP. We had a del switch. The del switch only updates the counters to the control plane every 14 seconds. So we have to pull that data, retrieve the data from the switch every 14 seconds. And INT, as I mentioned, is per packet. So we solve every single packet. So we can see here that we created on purpose 5 bursts of 40 to 50 gigabits per second for 5 seconds, because that's pretty much what the science driver that I presented at the beginning is going to do. But this will be all night long. So take a look, the difference of visualization. First, for those bursts, when you have INT, you get to see when they start and when they finish. And then you can count here 5 seconds. You see that there's a gap, and you can see the maximum utilization around 45 gigabits per second. When you do this for SNMP, since that data, that amount of data is spread between the moments that you collect that data, you can see that there is no precision. And you can see that SNMP is reporting only 13 gigabits per second. So you can clearly see that SNMP only gives you kind of an information that you had a data transfer, but doesn't tell you if there was a burst, that if that's continuous, that is like a steady data transfer. It only shows you an idea of how many bytes cross that packet every 14 seconds. And that's not the information we're looking for. For instantaneous egress key utilization, I want to show here on the left side, there's a graph with an average buffer utilization or queue occupancy that we see in our network. So this comes from the production. So you can see that in the average that you have 10 kilobytes, maybe let's say the maximum 40 kilobytes of data in the buffer. So those devices that we're using have 22 megabytes. And eventually you get to see that there is a congestion, and the congestion now goes to the megabytes time scale or size scale. So when we have this situation, I'm going to show what led to this, but this is like 2 flows trying to use the same outgoing port. And now you can clearly see that there is a difference. On average, you're not supposed to have that much buffering, but now you have a problem. So what caused that problem, how long the problem lasts, all of this is provided through INT. The sources of data that I mentioned before, here on the left side, there's an average hop delay, and look at the time scale. This is microseconds. So in an average, we have 1.5 to 2.25 microseconds delay per switch, right? But in the same moment, when we had the buffer at 2 megabytes from the previous slide, then you get to see that the buffer, or I'm sorry, the hop delay, it reached almost 65 milliseconds. So we're talking about more than 10 times slower when you don't have delay. So we all know that devices have memory gets full, and because it gets full, then you introduce delay. But this kind of information is provided per packet. And the scary part is that you can see here that just one switch introduced the same delay of the packet going through an optical fiber from Brazil to Washington, D.C. So it's inside the same switch, it took the same time that a packet using propagation delay from Sao Paulo to Washington, D.C. So you clearly have to do something about it, right? So you clearly have to keep mapping this. And this is the kind of delay that if you have a ping running on the CLI, you get to see the difference. You get to see the 100 units is even the millisecond units varying because of this. So what were the challenges that we had in this project? So a little bit of context for those who were not here in the previous presentations. The AmLight-INT, it was funded by NSF in 2018. That's how everything started. It's a collaboration between FIU and NoviFlow, which is a software development company that does software development for Tofino chip. And the NoviFlow was the operational system that we use in our SDN network. And then it made sense to ask them to expand their operational system to do this, to support INT, because the switch is a Tofino, is a programmable switch. And we developed the collector side, which is the side that receives the data and does all the magic with that data. Again, a characteristic of the switch is a barefoot Tofino chip. Most of you probably heard on the news, there's barefoot Tofino 2, there's Tofino 3 coming out in maybe 3 or 4 years. But this is a fully programmable chip. It has 32 100 gig ports. Some of them have 64, but ours have 32 100 gig ports. And back then, this INT specification was 1.0. Today, there's all the way to 2.1. We're now working towards expanding that right now because we're very satisfied with the kind of information, but eventually we're going to get there. So,
Jeronimo?
I'm sorry. Yeah, go ahead.
There's a question that came in that may be relevant. It's from Hans. Going back when you were talking about the telemetry packets themselves, how much data does each telemetry stop add to the packet? How big does a packet? I'm sorry?
24 bytes.
Okay. And how big does a packet going through the entire system become? Is there a problem handling that overhead?
So let me see. There is a slide that talks. Yeah, that's exactly the slide that I'm going to present now. So, well, good point. Each switch adds 24 bytes of metadata. It's 4 bytes for the timestamps, ingress timestamps, 4 bytes for egress timestamps, 4 bytes for the 2 bytes for ingress port, 2 bytes for egress port, 4 bytes for hop delay, 4 bytes for queue information. Yes, so that's it. So in total, we have 24 bytes per switch. At AmLight, using the science driver example, from Chile to the US, you go usually from 4 to 8 switches because there's every site that has 2 switches, at least 2 switches for redundancy. And just to give some numbers, here's an example. You can have reports plus, if you account all the telemetry from 8 switches, for example, plus the TCP/IP header, plus the telemetry data, telemetry header, all this, it can lead all to 300 bytes for the telemetry reports. But for the packet, for the user packet, it's only the telemetry that is added by the switch, and the first switch adds a header, which is 12 bytes. So the total size of the packet, the total length of the packet is going to depend on how many switches you have on the path. The Tofino chip has the MTU of 10,000 bytes. So and since in the academic side, we usually use 9,000 bytes packet for payload, then means that you have almost 1,000 bytes for overhead for telemetry. But we're trying to cap it, and the specification also suggests that don't add more than 10 metadata. If you have to use more than that, maybe split between the switches in the middle. So using like Internet 2 use case that has 30, 40 routers, maybe let's say there's 15 the path between Miami or between Florida and Seattle, then just pick 10. It would be ideal, but you can go as much as almost 100. Yeah, there's plenty of space for telemetry data. So this is part of one of the challenges that I want to talk about is that picture a flow, 100 gig flow with a 9,000 bytes. Then there's this generates 1.5 million packets per second. So this is what the computers use. No big deal. We're kind of used to that. But now we have to keep in mind that every packet generates a telemetry packet. So that means that we have to process 1.5 million packets per second of telemetry data, each one with up to 300 bytes. So in some cases, it can an 100 gig flow can generate 4.5 gigabits per second of telemetry alone. So since this is sent by one switch, is the destination switch of that flow, there's the switch will add a source address and a destination address that is not going to allow you to have hashing. So that means that all that packets are going to get into the NIC of the collector, and it's going to get into the queue of that NIC, and then it's going to be assigned to one CPU of that node. So then the challenges that we had at the beginning was, so how can one core process how many packets? 1.5 million packets per second. So right away, we understood that, well, this is not normal for normal hardware for a user application. So we had to be creative. And the creativity came from this thing called Express Data Path. It is a functionality that comes now in the Linux kernel after 4.15. Basically, it's a layer that you can execute some code, networking code, before the packet lands on the Linux networking stack. So this makes it very simple, very fast. It's very limited in terms of what you can do it, because you don't want to crash a packet, or you don't want to crash that code so low level in the kernel, then you crash the whole node. So this is going on like for almost 5 years now. The Linux community is using this a lot. There's plenty of publications, and the most famous case is Cloudflare, the DOS mitigation, where they managed to do like 20 million packets per second per computer, per node. And they use this for the DOS mitigation because none of those packets land in the networking stack. They are dropped or at the NIC or in the lowest level of the Linux networking stack. So just as a comparison, when we're doing this using Python and C, we're capable of process 5,000 packets per second. With XDP and one CPU, 3 million packets per second. And this is, depending on the case, you can go a lot more than that. So this is the CPU using 15, 20% utilization. And here's 100% utilization. So then this is clearly like an improvement. It's something that we had to switch to, because otherwise we'll not be able to get to the point where we are right now. You see there's another question, Jason? No? So let's move on.
Yep, we're good. Sorry about that. I thought I was unmuted, but I was not.
So go ahead.
Oh, no, there's no more questions. You're good.
Okay, okay. So challenge number 3, it's storing the telemetry reports. So you can picture this. If we're struggling to receive, which is something that you just have to access a memory buffer on the NIC or on the operational system, imagine the challenge that is storing that data, right? So right away, we learned that if we want to make the solution efficient with XDP, then we have to process as much as possible in the XDP. And we learned that 99% of the packets that follow a packet, they have pretty much the same data in terms of telemetry. So what we started doing was we found this in the literature that someone using this model here, they define an upper bound and a lower bound and an upper bound, and they only record the first packet from this interval. And only in case it changes, for example, this solid line here, then you record. And everything that is in between those bounds, then you don't do anything. And then if you go out of bounds, then you set it as a new target, and then you keep logging only the things that are outside of those boundaries here. So doing this, it made the system a lot scalable. And what we did to set the lower bound and an upper bound, for example, for queue occupancy, was a variation of more than 20 kilobytes. So if it changed, if this is the number that we start with, if it goes lower than 20 or higher than 20, then we log. The same thing for hop delay variation. If if we set the first one, the first packet, if the difference is more than 20 microseconds up or down, then we log. Delay variation, 15 microseconds. So all of this is customizable. So it depends of the more precision, more granularity you want, more CPU and more storage you're going to use. So then you have to find a balance, because all of this goes into a time series database. And these numbers, for now, they're good. And also every time the flow path changes, then we record this. And this is just like when you have fiber cuts or different hashes, this kind of stuff. So this doesn't happen a lot. And then there's the challenge by the nature of INT, by the nature of stream telemetry or event-driven monitoring. So when you have event-driven monitoring, you depend of an event taking place for you to do the monitoring. But what if you don't receive an event, right? What if you don't receive a notification? Then there's always that kind of question, oh, is it because there's no event? Is it because there's no traffic? Is it because my system is down? So then you have to create approaches that if you don't get any change, if you start seeing that all your graphs are zero, like are empty, you have to find ways of understanding why is it zero? Is it zero because it hasn't changed? Or is zero because there's no traffic, or because my system is down? So when you do this monitoring based on events, then you have to take this into consideration. So one of the things that we do going back to this, let's pick the first example here. When you have a Q occupancy variation, and that variation, this interval here, doesn't get out of bounds here. So you stay inside those two limits here for more than the interval that you're looking for, then you're going to see that there's no data. So if you have let's say a Grafana portal that has the monitoring, it shows this, then nothing changed. That means nothing's being added to the database. So there's no updates on the database since the timestamp of this measurement here. And that's the part, what we do here is then every second, even if there's no change, if it's inside the borders here, we log it again. So if it has passed more than 1 second since the last measurement, then you log it again. But at least you're not going to log the other 1.4 million packets. You just log one every second. And this is only in case your profile, your measurements is still within those borders here. So then you have the challenge that we get from researchers. There's a lot of people doing research that uses machine learning and artificial intelligence that they asked us, I need a grounding truth for learning algorithms. My machine learning algorithm needs to know what is a DDoS. Can you try to send me all the telemetry that it was collected from the time that you had the DDoS and for me to use that? At this point, no, we cannot, because as I mentioned before, it's hard enough to process those packets. So if you have to store each one of them, it means that you have to do a transition from a context switching from the kernel space to the user space that is going to consume a lot of CPU and is going to delay the processing of the next packets coming. There's not a lot, there's no threads and process when you're working in the XTP. So you have to be very mindful of what you ask the code to do it. And you're limited to only 4,096 assembling instructions. So there's not much to do in this case. But so as an example, picture again, the Vera Rubin telescope, 5-second data transfer, or only 13.6 gigabyte, right? That's going to generate 337 megabytes of telemetry data. And we'll have, let's say 6 to 6 in the morning, 1,334 observations per night, which leads to 450 gigabytes of telemetry data per night for just this flow. So you can see that there's challenge that comes with this, right? So how do you save all those gigabits per second of data? Where, how long do you store such a data? How do you keep privacy? What data is really necessary? So this is one of the things that it's hard to answer if you don't know the questions. What you're looking for in this telemetry data. Are you interested? Can I drop, for example, the TCP timescale or sequence number? And you're gonna say, no, because I do, like I'm monitoring TCP data transfers. Oh, can I drop the hop delay? No, because I'm doing this for QoS and for voice over IP. So eventually people are gonna say, well, keep everything. And then we figure it out. So yeah, if we store everything, then yeah, we're not going to store anything because that's going to be impossible. So this challenge is wide open. We're not very focused on that one. If you have interest in participating in this, if you have students or anyone interested in doing this, please contact us. We're more than interested in provide help for you to do this yourself. So now talking about the deployment. So how is this working in AmLight? So every site that has the new solution has Tofino switches, has a management network, and has a telemetry collector. So all the data from all the switches, because users are connected to all the switches. So every switch here might be the last switch in the path. So all those switches send the data through a separate network that has to be high performance to the telemetry collector, which that processes everything. So currently we have a Supermicro 1 rack unit, has 2 sockets, 2 CPUs, 16 cores, 3.1. So this solution requires the higher clock possible that you find. So if you just go, if you want to parallelize an application that has 64 cores, and then every core is 2.0, yeah, that's not the core that you're looking for, because it's very hard to hash these data. So then it's very possible that all the packets are going to land in the same CPU based on the nature of the traffic. And then there's the centralized controller that connects the dots between the collectors, the remote collectors, because each collector only has the view of one direction, right? So if the data goes from Chile to Brazil, only Brazil is going to export data. If the traffic goes from Brazil to Chile, only Chile is going to export the data, but every communication is bidirectional. So then you have to connect the dots here, and this is done by this central entity here. So the deployment per node, even with XDP, we had to do a little bit of a workaround. So the workaround was that we broke down the code that we had in 2 codes, and each code was specialized in one function. So picture this example here. On the bottom, we have the NICs. So picture there's a layer here with the NIC, the actual hardware, and then you have the kernel space, and then you have the user space. So on the NIC space, we have these natural norm NICs, which are programmable NICs. Then we push the code to the NIC. So that threshold, the boundaries that we're talking about, this is done by this threshold enforcer. So this guaranteed that only packet that had a significant change since the last packet are allowed to go to the next step, which is inside the kernel space. So this we use for queue occupancy and hop delay. And then we're going to start doing the math and then processing the packet a little bit at the XTP layer. And then we push this to the user space when we think is the case to be stored. And then this application, the user space, is stored in InfluxDB, which is a time series database. The other NIC, which is a Mellanox NIC, then these packets go directly to the kernel because we do only interface counters. It's like an SNMP. And then we only store and drop those packets. And then there's a user space application that keeps like pulling that data from this module through shared memory and does in an interval of 500 milliseconds. So every 500 milliseconds, those counters are updated into InfluxDB, and then we have Grafana as the network visualization approach. The user space is all written in Python, everything else is written in C. So the demonstration that what we did for supercomputing basically was sending traffic from Santiago to Sao Paulo to Boca, Miami, and to a node that is in Miami, which is the path that we have, well, full control, but simulating the path that the telescope Vera Rubin is going to follow. So this node is exactly at Vera Rubin data center. We have an 100 gig node over there. So this pretended that this black line is VLAN 309, and this is the science traffic. And then here in Miami, we create the congestion traffic using VLAN 3500. So again, this is an illustration. The IP address is the VLAN. What we did on purpose was this node here is a Tofino node. We forced both flows to go through the same port. So this one was using 100 gig. This one tried to use 100 gig. Both were using TCP, and they were sharing the port 25. Okay, so this is what happened. I know that maybe the color is not the best, but Grafana, when it exports the snapshot, it gets like dark mode. So here I'm using just one example, one data transfer that we did. This goes from 2 in the afternoon, 2:14 in the afternoon to 2:20 in the afternoon. So then this purple here is the science traffic. You can see that I was almost getting 100 gig. And then we started the congestion, the noisy traffic. And then they start sharing exactly 50 gigabits per second. And then we stopped the congestion, the noise flow, and then the science application went back to the maximum capacity, which is 100 gig. And here we're monitoring the VLAN utilization. Those other VLANs are production traffic. So let's focus on this too. You can see that the science traffic created 7.7 terabytes of data in this, again, 6 minutes interval. Yeah, 5-6 minutes interval. And this one, the noise was almost 2 terabytes within the same interval. So here we have the monitoring from the switch port, the queue that was used here was Q0 and the VLAN. So you can see that we're using visualization. Yeah, forget it, the maximum here. There's a mistake that we had a mistake at that point. But you can see that the monitoring is done per VLAN plus queue plus port plus switch. So here underneath we have just per queue and per port, so it's pretty much the same. So then you can see that the port, this is port 25, and port 25 is always 100 because there are two flows of 50 competing. And then this one is packets per second, same thing per queue per VLAN, but now the information that we never had before. So this is the queue occupancy. You can see that in a moment that there is that we start seeing two flows sharing the same resources, the buffers right away increased all the way to 2 megs. And then it kept like this, and then we stopped the congestion, it dropped again, and then you see that the flows kind of calmed down. There's a few spikes here, but it kind of calmed down. And there are other flows as well. You can see there's production traffic in parallel. And here on the bottom, you can see the hop delay, how the hop delay increased from 1.46 microseconds all the way to 150 microseconds during the times of congestions. And this part here, the straight line, is that line that I was talking about, that it got to this point and then didn't change anymore. So then Grafana thinks that is the same value, but it's just because there's no measurement. The Grafana used the last value that was logged here. But you can see that after the congestion ended, then it kind of calmed down in terms of hop delay. Here on the bottom, we have the telemetry packets per second. So this is telemetry. This is not production. This is not user data. This is telemetry data. Almost 2 million packets per second. And the one in yellow here shows how many packets contain different in the content that was meaningful for us to record. And it got to a point that was 440,000 packets per second. But in general, you can see it's very minimal. The profile doesn't change unless you start having congestion those ports. Let me see what comes next. Okay, so before I go next, let me show you, this is now the production. This is for us right before the presentation. Well, it was this morning, in fact. So I got like 3 hours. Yeah, 3 hours of measurement here. And although you can see that most time this link and this switch is very calm, like sometimes not even a gigabit per second, we have multiple peaks that go all the way to 63 gigabits per second. This one goes 68. And those peaks here, when we look at, I'm gonna like overlap here with the Zabbix that uses SNMP, exactly the same time interval. Yeah. So then you can see here that Zabbix only reported us to having peaks of 8 gigs because that data, those 20 seconds, and this is not artificial data. This is not something that I created. This is something that happens in the network. This is traffic going to internet too. So this traffic here is only reported in SNMP as 8 gigs because look at how long this data was, like it was considered to be for almost 4 minutes. And when in reality, it was, I was zooming in the future here after, but it was 14 seconds. So this 14 seconds peak here that achieved almost 60, let's say 64 gigs, it was showed here on Zabbix as 8 gigs. The second one was more than 40, was showed as less than 7. And then you can see that some of the peaks don't even like showed up because it's so spread here. They're so small, they're like microbursts sometimes that we don't get to see using SNMP. But the point is, what I want to show is that if we didn't have a 100 gig network, then you would say that a 10 gig port would be enough, right? Because look at my time scale here. The maximum here is 10 gig. And then you said, oh, so 10 gig should be enough because you never use more than that. But because we have more than 10, we have 100, then those flows managed to do whatever data transfer that they wanted to do in 14 seconds. And if it was capped to 10 gig, probably gonna last a lot longer and then maybe affect their science flows, which I don't know what the science flow is here. So I'm not gonna make more considerations than that. But so this is again from production from this morning. And you see here packets, and you see what I want to show is the buffer utilization, because even though there was like 60 gigabits per second, there's nobody else sharing those resources. So there's no buffer. It's less than 20 kilobytes. If you consider that every packet is 9,000 bytes or 9 kilobytes, that means there's only 2 packets in the buffer, right? So it's no big deal at all. The network don't have any problem based on those numbers here. And on average, you can see the most packets are 1,500, which is the standard for our next day.
So Jeronimo, before you scroll down any further, going back up to the actual utilization spikes there, have you been able to track down what that could be? I mean, just my, rough looking at that looks to me like that would be monitoring traffic from perhaps a persona node, since it looks rather regular and it only lasts for 10 seconds. Has there been any effort to try to figure it out?
We have efforts, but we have not gone deep into this. It's not our persona nodes, I can tell you for sure, because ours are 10 gigs. So this was the first thing that we look at. It's 20 seconds. It looks like a persona test, a bandwidth test, but we don't have any persona node that is 100 gig. We know that we create in the past routines between that node in La Serena, where the telescope is, with the nodes in Miami, but that was for tests every 4 hours, or no, every 2 days, in fact. But anyway, that one would be 100 gig because we know we can generate 100 gig. So this one is still up for investigation. The reason is because we don't have, this is coming from Brazil, and we don't have the switch in Brazil yet operational for telemetry. So we haven't had the chance to see which port this is coming from. If we go deeper, we will find it using the flows. We have flows. But one of the things we're doing right now is to create a monitoring system that when it looks at this, it's going to request the telemetry system to be more specific about IP addresses inside, not just the VLAN, but also explore information about what was the IP address or the top 10 IP flows that were within this interval. But at this point, and I don't know exactly what was it. But I'm very happy to see those, I can tell you that. Moving on. So this is the hop delay. You see that there were peaks of 80 microseconds. One of the things that we learned is that although all of this is done in hardware, sometimes there is weird results, right? So if there is no buffering, if there is there's no traffic in this interval, why there was like these spikes of a delay, right? Sometimes you see spikes of delay out of nowhere. So this is probably a hiccup somewhere, but we're investigating this. We have tickets open for this with the manufacturer. But I can guarantee you that troubleshooting this on the hardware, it's very hard, very hard. Telemetry packets per second. So there's, you can see peaks of almost to 1.3 million packets per second and up to 100,000 packets per second of change and some damage. So let me zoom in just one of those. So just for us to see the precision of this, we have a couple minutes. So you can see exactly starting 10 hours, 29 minutes, 22 seconds, and 620 microseconds, milliseconds, I'm sorry, and then goes for 2937. 29, 22, yeah, 15 seconds, yeah. And you can see all the intervals is not just one line, straight line. Every 500 milliseconds, we capture this data, and we can see this for like with a little bit more of information. You can see here the buffer utilization at that point, reaching 15 kilobyte. Hop delay for that interval, 3.5 peaks of 3.5 microseconds, 1.25 million packets per second of telemetry. So just to wrap it up here, what we're planning to do in the future, we have two projects that are strongly based on the telemetry data. One is the next generation of AmLight. AmLight, the previous project that was when we started this ended in 2020. So in 2021 to 2025, we're funded again. And what we're doing is creating this concept of closed loop network orchestration, where the switches will export telemetry to this telemetry collector that we target today. And now we're creating this learning system that I was mentioning, that once he sees a spike, is going to ask for more precise, like more information. So this learning system will also send network intents to the SDN orchestrator that we're developing, and these SDN orchestrator will send instructions to each switch, and then those switches will keep sending the telemetry, and then the learning system we're going to evaluate, and if there's a need to make change, it will make the change. So then we keep this closed loop based on the telemetry. So it's the network managing the network. The roadmap that we have for this project is that by the end of this year, we want to complete this cycle in less than 5 seconds, and then year 5 in less than 500 milliseconds. So whatever condition that we document and create a policy for that takes place, we want to react to this in less than 500 milliseconds. But you can see here that even if we do 5 seconds, we probably address the goal of the science driver at the beginning. We can fix something within the quiet window between the data transfers. And if you get to 500 milliseconds, we can even maybe fix something during the data transfer window. Maybe instead of completing in 4.5 seconds, it's going to complete in 5.5 or maybe 6 seconds. But we know that we have the tools to react very fast. We'll have the tools to react very fast to these conditions. So there is a CI Lunch and Learn, another presentation on March 18th that I invite you all to attend, that I'm going to be presenting this project. Not the results, we're still in the beginning of year 2, but everything that we're planning to do for this, for the next 4 years for this project is very interesting. And then the other project that is consuming telemetry, is benefiting from the INT, is the CC Star integration QFactor. It's a collaboration between FIU and ESNet. And the goal is to not remove the telemetry, let the telemetry land on the destination node. The destination node will know everything about the path that is between those two nodes just for their flows. And then they could make decisions for tuning or for whatever they want based on the accurate information from the network. So if they want to do like buffering, occupancy guessing, like some protocols do for TCP, or if they want to do based on the delay, or if they want to do based on packet loss, there's no guessing anymore, because the switch will tell you exactly what was the condition of that switch when that packet was in that switch. So then you can get to a point that you can do very precise tuning for those nodes, and they can consume the telemetry data to do whatever they want. So there is also a plan. So this is a plan for another CI Lunch and Learn. Maybe in April and May, there was like changes in the team. And in fact, this presentation was supposed to be today. This was the original one for February 25th. But Jason was very nice and allowed us to postpone this a little bit. So this is the content that I wanted to present today. Is a wrap it up of those 3 years of project. I promise this is the final time that you're gonna hear me talking about INT. And now the future presentations about what we're doing with INT, but not INT itself. Please let me know if you have questions.
All right, well, thank you for going through all of that, Geronimo. Really good stuff. It looks like we have a hand from Marcos. So Marcos, I will unmute you if you would like to answer once I figure out how to do that. All right. Go ahead, Marcos. You can unmute yourself.
Hi, Jason. Hi, Jeronimo. Can you hear me?
Yes.
Okay. So I think it's not the most important part. That's where I got some ideas. When you were talking about researchers wanting some raw data about telemetry, one approach we are doing a proof of concept in RNP is to try to have a sink where you send raw telemetry that is connected to a RabbitMQ, where a researcher can authenticate and request access to a specific kind of telemetry. So you're not storing the data, but you're having a cache, a small cache. So if during a live stream, a transfer, he wants to get the data, it's possible, but you're not trying to save everything for everyone. So it's like a way of a server self, do your own data set, something like that. And when we have something working, I can show you if it's something that maybe could help on that kind of issue, because it's kind of a light solution, not a complete solution to this kind of problem.
Yeah, so in fact, the first solution that we built was using RabbitMQ to do the same thing. And when we saw that under stressful situations, when you have a lot of telemetry, RabbitMQ alone was dropping 95% of the packets, even when you do it in the synchronous mode. So, and RabbitMQ is only, it was, at least in its documentation, is planned for hundreds of thousands of messages per second, but not millions of messages per second. So it all depends on how much traffic the user is generating, because then the telemetry is going to be proportional to that. So if he's generating more than, based on the test, if he generates more than 5 gigabits per second, a RabbitMQ is not gonna work, because moving that data from the kernel space into the user space, and then from the user space in your application in place in RabbitMQ, we're losing 95% of the telemetry data. So one of the things we're doing right now is with Kafka. Kafka is planned for millions of messages per second, but there is still a challenge: is how do you get from the kernel into Kafka without minimizing the context switch? So doing this transition, when you send the packet through the networking stack on Linux node, that's what kills those applications, because then the packet has to go through the whole stack. And once it lands in the user space, and keep in mind, all of this is following the same CPU. And then once it does the context switch, it gets to 100% of CPU, and then that's it. There's no space for placing a Kafka queue anymore. I'm sorry, and a RabbitMQ anymore. So we have the code that does that if you want to see, but it's limited to 5,000 packets per second. That's the maximum that we managed to get.
We are not working with in-band telemetry yet. We're just doing it for
which I know, I'm not sure about Tofino 3, but we want to go to Tofino 2. The main thing is Tofino 2, it has a lot of benefits from the programmability perspective. It's not proportional, it's not like a double, although it has like 4 times more performance, it doesn't have 4 times more capabilities. For example, the memory improvement is just a little bit, is maybe buffering is like 2 more megabytes in terms of SRAM memory increase at the double. So, but it's a 400 gig port. We're looking, when is the best moment for us to justify this? We don't have that much bandwidth to justify migrating everything to 400 gig ports. But we know it's real. We have seen the bugs, but those bugs are not for sale yet. So if it's vaporware, I don't think so. But it's kind of weird that it's very late.
Great. Well, that was all the questions. So thank you so much, Jeronimo, for giving your time and going through this today. I get a chance, I'll make sure I get these posted. And then if you do have any links to public dashboards or anything that you can make available, I'll make sure to send those out as well.
Yeah, I'm sorry.
And
in the presentation here, I'll keep this snapshot in case you want to go through it. But there's an expiration date, so I don't know how to control that. But if you're available looking at this right away or for the next week, will be available for sure. Thank you, Jason. Thank you all that attended.
Yeah, thanks everybody. And I misspoke at the beginning of the talk. I thought that we did have one scheduled for next week, but it was moved because the presenter had a conflict. So we will actually be on a 2-week pause, and then we will get to hear from Jeronimo again about the other project that they've been working on with the automated, or I'm sorry, the
Closed loop
autonomic network architecture. That's going to be a hard one for me to internalize and say the right way. So thanks everybody, and we will talk to you in a couple of weeks.